So let's go back now and connect this to something we talked about in section 1.9. Remember that matrices can be identified with linear transformations that act upon vectors through matrix multiplication. So let's spell that out a bit in a specific case when we've got two matrices, A and B, and you can see I've written out the dimensions here so that they can be compatible through matrix multiplication, and we'll see why in a moment. But for starters, let's just convert these matrices into linear transformations. So let's start with B. B is an n by p matrix, so that means it determines a transformation, which I'm going to call S, going from Rp to Rn. And the way that it behaves, the way that it converts an input vector to an output vector, is it multiplies it by the matrix B. So if I plug a vector into X, what it's going to give me back is the product of B with X. Okay, and the dimensions work out through matrix multiplication because X is a column vector here, right? So it's a P by 1 matrix, and B is an n by p matrix. So the dimension diagram will be satisfied, and the product, the result, is going to be an n by 1 matrix. So this really is a well-defined operation. It's going to take an input vector from Rp and give me back an output vector from Rn. And let's just draw a picture here. This is just a rough picture. It's not going to be anything gorgeous. So let's say this is Rp, and we've got a vector here. And let's draw a similar picture for Rn as well. And then we'll also do one for Rm in a moment. But for now, let's stop here. We've got Rp and Rn. So I've got another vector in Rn, which I can write down as b times x. And what S is going to do is it's going to send x to the product of b and x. Okay, that's how it's defined. That's what it does. Okay, let's do the same thing now with t. Okay, not t, sorry. Let's do the same thing with A, is what I meant to say. And we'll define a transformation T that is identified with the matrix A. So if I want to convert an m by n matrix A into a transformation, that transformation, which I'll call T, is going to go from Rn to Rm. So it's going to take as input an n-dimensional vector, and then as output, it's going to give us back an m-dimensional vector. And the way it's going to compute that is it's going to multiply that vector by A. And again, the dimensions work out. If A is m by n and x is a n by 1 vector, then the product is going to be an m by 1 vector. So it really truly will give us back an output vector that's in the codomain. So I'm going to add Rm to this picture now. And what's going to happen here? Well, T, if I apply T now to the output vector from S, so let's back up. We started with a vector X that was an Rp, and we plugged it into S. And what does S do? It gives you the product of B and X, because X is what we plugged in. So that takes us here. But now what if I plug Bx into T? So I'm going to take this function here, and I'm going to plug in B times X. So I'm going to plug in B times X here. What I'm going to get is actually B times X for the X part. Instead of X, that kind of sounds awkward. For our input parameter, we're going to plug in B times X. So what you're going to get over here is A times, then in brackets, you'll have B times X. Let me write that down. So we'll have A multiplied by B times X. Okay, and let's take advantage of this property up here, which says that if I have three matrices that I'm multiplying together, I don't need to worry about where I have the brackets precisely. I can shuffle the brackets freely. I can't change the order of the products, well, because then the dimensions might not even work out and the product might not be defined, right? But I can shuffle the brackets, and here's what I mean by that. I can say that this is just equal to AB times X. And that's actually what I'm going to write here. I'm going to write AB, actually I'm going to write it over to the side. Here, AB times X, like that. So that's what T does. If you plug in B times X, you're going to end up getting AB all times X. So now what I want to look at is, well, what would happen? Well, I mean, this picture should look a bit familiar. This is a little bit like the diagram you typically will see when the first time you encounter function composition, right? What if I wanted to go right from X all the way to AB times X? I could just, that kind of didn't, there we go. This is really the same as T of S, right? That's what T of S is doing. First, plug the input value into the function S, then whatever you get as output from that function, which would be namely this, plug that into T, and then you get your final output. That's exactly the behavior of the composition of T and S. So T of S as a function. So what you see here is that, let's go through this carefully. So T of S of an input vector x is by definition, this is just by definition of function composition, this is T of S of x. And now S of x, if I just look at the inside here, that's the same as B times x. So I have T of B times x, right? And then, well, now I look at the definition of T, and what does T do to an input vector? It multiplies the result by, it multiplies the input vector by A. So I'm going to have A times bx, and then finally I do this bracket shuffle, and I can write this as AB times x. So what's the point of this? This is true for any x in RP. So what this tells you is that if you compose two linear transformations, that the result is going to be a linear transformation. You can check that. You can prove that carefully. It takes a little bit of work, but you can do it. So if the composition is a linear transformation as well, it should have a standard matrix. And it turns out that if you want to get the standard matrix of the composition, this we just checked. It's going to be the product of A and B, where what's A and B? A and B are just the standard matrices of the two linear transformations that you composed. Okay, so that's what this fact is summarizing down here. This is essentially what we've just shown. If you have two linear transformations and you want to compose them, the standard matrix of the product is just going to be the product of the two standard matrices of the functions that you composed in the first place.